There we go. My sound okay today?
Yeah.
Awesome. Thanks. How's everyone doing? It's good that you're doing good. Hopefully everyone has power back and things. I had a few people email me last time saying that they couldn't come to class because their power was out because of the wind. So hopefully you are all good on that front. It's definitely a lot less windy today. So. I think both cats are sleeping, so hopefully no interruptions today. Also, hopefully nothing caught on fire with fireworks and the Dodgers. I definitely saw some videos and pictures on Twitter of a lot of flaming palm trees, as you would expect. Hopefully nothing in your neighborhoods. Wasn't anything that I noticed fire-wise here in Northridge, but definitely a lot of fireworks.
Excuse me, Professor?
Yeah.
Is it all right if I can leave early at around 3 o'clock?
Yeah, that's no problem. The lecture will be posted on YouTube later, so you can catch up on whatever you missed there.
Okay, thank you.
No problem. If anything, it's like way less distracting when you're in Zoom because you can just log out.
No, yeah, I just wanted to let you know beforehand.
Cool, thanks. Diana, I see you in here more than once. Is everything working out okay?
Yeah, sorry. It's because my laptop isn't so loud and I don't have my headphones with me, so I'm using my laptop to like look at the screen and my phone to hear
okay.
to hear you.
Okay, cool. All right, well, it's 2, so let's get started. See a smaller crowd today. I'm guessing some people probably did a lot of Dodgers celebrating and maybe don't feel like being in class. But anyway, we're going to pick back up where we left off last time. Actually, before I finish with our last literally 3 slides about sedimentary rocks, so our main topic today is going to be landslides and mass movements. But does anyone just have any general questions, concerns, things, etc. before we get going? Our next test is on the 9th, I think. Hold on, it's that Monday. It is, yes, Monday, November 9th is our next test. And so like all the others, it's going to be, a 30 question multiple choice test with a couple of extra credit points at the end. Like all the others, we will have, a 20 to 25 minute review session beforehand, and then you'll do the test on Lockdown Browser, which brings up a good point of, so last time there were some people who like Lockdown Browser worked fine the first time and then was not working very well the second time. So I would suggest that even if you got it to work perfectly for both tests so far, once we get close to that day, like earlier on the day on the 9th or even maybe on the 8th, make sure it still works with that fake test that's up there, just so it's not a panic situation when we start the real thing. But yeah, the next test is going to have all of the sedimentary rock stuff we just had over the last 3 lectures. And then it'll have the landslides and mass movement stuff from today, the rivers and floods stuff coming up on Monday, and the glacier stuff coming up next Wednesday. So basically all of the sedimentary and surface process stuff is going to be on that test. Cool. Does anyone have any other questions or concerns? And if you do think of any later, you can just put them in the chat or ask me at the end or send me an email. But I do kind of want to get going. Actually, yeah, the stuff for rivers and streams, the vocab and study guide, and those are all up already. So because we have 3 new topics real quick, landslides and then rivers and then glaciers, there's going to be like vocab stuff each time. But even so, but I'm trying to keep them to fewer words and keep the quick quizzes to fewer questions so it doesn't take up too much more time. But anyway, the first thing I want to do is just finish up with sedimentary rocks, because we got a little bit behind last time because I was talking about my bad internet connection. Although I will say again, if I get if the thing gets disconnected, I'll email you on my phone about what's going on. But anyway, we spent all of last time talking about the different environments in which sedimentary rocks form and how things like the movement of water and the speed of movement and whether the ocean is sitting still or crashing waves or whatever, how all of the movement of transportation mechanisms and the environment in which things are deposited affect the kind of rock. And so most of that was focused on clastic rocks because clastic rocks are the most common sedimentary rocks and form in a lot of different environments. But at the very end, we got into the other 3 kinds. So we got into biochemical sedimentary rocks, which are consolidated from calcium carbonate-rich shells of different critters, or sometimes silica-rich shells of plankton. And then we talked about organic sedimentary rocks, which are things like coal and oil shale, things where material like from mostly dead plants, sometimes dead animals, but mostly dead plants, where different parts of it are not able to decompose properly because there's either too much sediment or not enough oxygen or both, and those turn into fossil fuel rich rocks. And so the last one that we didn't quite have time for is chemical sedimentary rocks. And so those form from, and so all of them have chemicals in them, minerals or chemicals, but whoops, my watch is trying to talk to me. Chemical sedimentary rocks in particular form from minerals that precipitate out of solutions. So if you think way, way back to when we were talking about how minerals form, and one of them is how crystals might, like atoms might be in a fluid, whether it's water or even if it's lava actually, and then those will gather, and like if there's something like a string in the case of rock candy, or like the wall of a cave or whatever, then as the water flows over it, the crystals will start to collect and build up on that thing, that sort of seed, if you will. And so so chemical ones are basically the minerals that are left behind when the fluid is gone. And there's 2 major, well, actually, before I go on, does that make sense? So these are actually very often just like rocks that are made of one kind of mineral because of that. So it's that in the exact same way that those minerals precipitate from solution, these rocks precipitate from solution. So this is something that even if it sounds a little weird, you've probably seen an example of it. Actually, I went in the wrong order. Let's go from this one first. So who here has been to a cavern like this? Like Mammoth Cave in the Eastern Sierra, or like Carlsbad Caverns in New Mexico. Has anyone been to a cave?
Yeah, in Lebanon.
Oh, cool. So what was it like?
Very
Like-
dark, and it kind of looks similar to this.
Yeah. So if you haven't, I see a no frowny face. There are some in California, especially in the Sierra. But yeah, so all of this is sedimentary rock. All of this is sedimentary rock that precipitated out of groundwater. This is basically a case that originally, like usually it's water that clears out openings under the ground to begin with. But in this case, that water that's doing that is full of minerals. In this case, usually calcium-rich minerals. And basically, as that water is dripping, it's leaving behind little bits of calcium. And so over time, as it drips and drips and drips, the calcium-based minerals just start sticking to each other and making these stalactites, which are the ones hanging down from the ceiling, and stalagmites, which are the ones sticking up from the ground. And so while there is some water in here and some of this is a reflection, these are also actually just generally very symmetrical, because the water is going to drip off the ceiling and leave little bits behind on the stalactites, but then it's going to fall onto the ground and then start building up a stalagmite below it. So all of this is just minerals precipitating from solution. And these are all generally the same kind of rock throughout, but they form these shapes because of the way that water drips and flows over the existing formations. So does that make sense? I should maybe put another thing on our forum of like cool places to go to see this stuff, but I'll think about that later. So that's precipitation from groundwater. That's water that's flowing through the ground under the surface. But the other major kind of chemical sedimentary rock are what's called evaporites. And so this is not ice. This picture is of salt. All of this is salt in the desert. It was hot out here. It just looks like ice. And so this is a case where rather than there being minerals, like rather than the water being flowing around, rather than the water flowing underground, this is a case where water will seasonally pool up on the surface. So like even the desert gets bodies of water sometimes, usually in the winter when it's wetter. And so in the winter, that water will fall and will have minerals in it just that is absorbing from other rocks in the ground. And also there are rivers in the desert that will flow seasonally and will bring in minerals from other places. And so while it's the wet season in the desert, you'll just have pools of water that are very mineral rich, just kind of hanging out. But once the winter's over and the really dry part of the year sets in, the water is going to evaporate easily, but you can't exactly evaporate salt at the temperature of just even the hottest desert temperatures. Like salt doesn't evaporate. So what happens is the water leaves and the minerals stay. And so this example really is just salt. Like I took this picture and yes, I did taste this rock and it was salt. But there are other places where you can get some really wild minerals that are evaporites, that are much more unusual stuff. But salt's the most common one. And so this is just what's left behind when the water goes, hence evaporite, evaporation. Any questions about that? Yeah, I tasted it. It was salt. I think, were you not there in the lecture when I talked about why geologists lick rocks? We'll get back to that later. One of the best ways to tell whether something is salt is to lick it. Geologists are, yeah. Sometimes we say this stuff in class for shock value, but sometimes it's actually a really useful way for telling what something is. Oh, right on. So those were literally the last two slides about sedimentary rocks. Does anyone have any questions about either of those or about any of the other just general rocks and sedimentary rocks and depositional environment stuff before we switch gears and talk about rocks falling down.
Professor,
Oh yeah,
the lecture is up, right, for sedimentary rock?
yeah, this is already up. I put this up last time.
Right, thank you.
And I'll put up the landslides one today. Just whenever we finish a topic, it'll go up. Cool. All right, so I'm gonna switch presentations. So if you come back, screen share button. I hate that I lose the chat window every time I change my screen. Okay, so do you see a new PowerPoint now that says, what do you think of when I say landslide?
Yes.
Awesome. Okay, what do you think of when I say landslide?
Mud falling, or not falling, but
Rock falling.
sliding.
Yeah, rocks falling, mud falling, rocks sliding, dirt sliding, exactly. So all of those are correct. And so that's, yeah, it's another one of those examples where the word, this is a technical word, but it's also an extremely, extremely literal word. But as it turns out, a landslide specifically actually has a more specific meaning, which we'll talk about a little later. A landslide is just one example of something called a mass movement. So a mass movement is downslope movement of stuff. Rock, soil, mud, sediment, debris, ash, ice, snow, all the things, geologic material falling or sliding or rolling down is a mass movement. So mass in the sense of it's material, and there's generally quite a lot of it involved, and movement, it's moving. So a landslide is a subset of mass movement. But just if it's geologic material moving, then it is, especially if it's a lot of it, it's a mass movement. If it's just small, like sediment transport, not necessarily. Like you wouldn't call a river carrying sediment a mass movement, but you would call anytime just rock starts falling downhill a mass movement. So this is the word I'm going to use for just all of them. And what we're going to do today is talk about in general why rocks fall and slopes fail. But also we're going to go through some specific ways that this happens. And yes, there are a lot of videos in this lecture. It's kind of hard to have videos for sedimentation because it's such a slow process. But these are generally pretty fast, and there are videos. But I'm going to say mass movement, but your book uses some other terms as well. You're probably, if you start to read more about these in other places, you're going to see the term mass wasting or slope failure as well. And those mean the same thing. It's, in this case, just wasting or movement. It's going away, it's falling down. And slope failure is because this, with the exception of sinkholes, which we'll talk about at the end, it generally requires that there be a slope. But even sinkholes, there's kind of an interior slope. We'll get back to that. Does anyone have any questions about this definition, though? Cool. All right, so let me ask you another question then. So hills, they're everywhere. There are slopes. What do you think might make them fail sometimes? Gravity, absolutely. Just plain old gravity.
Water.
Yeah, water is crucially important. Wind definitely can. Most of the kinds of things we're going to talk about do involve water. Yeah, honestly, those are the big ones. Wind, water, gravity. Generally, you also need something to cause the slope to fall apart to begin with, which can be anything from the weathering processes we talked about before to just pre-existing weaknesses, also to things like earthquakes. And so this is very much a sedimentary process, both because it is a transport and deposition mechanism, but also because it tends to be the sediment that fails. This failure, it tends to be most common in places where the sediment is only loosely lithified or not lithified at all. It's just sediment and not even sedimentary rock. Or sometimes, if you remember how we talked a lot about sedimentary rocks piling up in layers, well, those interfaces between the layers, like where if you have like one kind of layer and then something else on top of it, the boundary between them is actually usually a weak zone and can be a place where things just move and slide. So mass movements both are affected by pre-existing sedimentary processes and also contribute to sedimentary processes on their own. Does that make sense? Cool. So if all of those things can make slopes fail, you know, wind happens all the time, water is around, gravity, we would definitely notice if that stopped. Why do you think slopes don't fail most of the time? Why can we still have hills if such common processes as wind and water and gravity can make them fall down? What's holding it together? What do you think?
Maybe plants?
Plants absolutely help, especially for things like mud flows, for things that are just involving soil and loose sediment rather than rock. Plants are actually a big help for that, which is kind of why when you have a fire and it burns all the plants and their roots aren't holding things down anymore, you're more likely to get mudslides. But what are some other things? Like think about, you know, there are plenty of hills around that don't have anything growing on them, like in the desert. What else do you think? And just even wild guesses. Like, don't worry if you have no idea, I will tell you in a minute. I just sort of, a lot of it is like, imagine you're the first person to see this happen. You would go, well, if this happened here, why doesn't it happen everywhere?
Evaporates?
So sometimes, so think along that line of thought. So it's not necessarily evaporates specifically, but what happens when, so what needs to happen for an evaporate to form?
Like the sun hitting it?
Yeah, the sun hits it and the water leaves, right?
Mm-hmm.
So is a bunch of dirt that has water in it versus a bunch of dirt that does not, first of all, are they going to feel the same?
No.
Now, are they going to weigh the same?
No.
Yeah. So a lot of it, a lot of that stability has to do with just kind of what angle can a slope exist at, given what it weighs, given what's in it, given how stuck together the interior of it is. So does that make sense? A lot of it is weight and angle and how stuck to itself that rock is. Like a pile of sand is not very stuck together. It's going to be able to much more easily just kind of slide down than a pile of solid rock. But basically this question of what keeps slopes from failing most of the time is, it's mostly a physics question. It's actually entirely a physics question. So it's basically the interplay between how stuck together that stuff is and the downslope pull of gravity. Like gravity makes stuff fall. It's not going to fall if there's no gravity. And so gravity wants to pull things downhill. Like if you put a ball on a slope, it's going to roll downhill. And so in this case, there are two forces that are resisting the gravity. And again, gravity wants to pull down. It doesn't necessarily want to pull along an angle. It wants to just pull down. But on that angle, you're going to have a couple of things. First of all, you're going to have friction. So this is the very same friction that keeps you from falling on your butt when you take a step. The friction between your foot and the ground is the thing that helps keep you up. It resists the pull of gravity on you. Or the friction between your hands as you try to rub them together and warm them up when it's suddenly cold after a hot summer. That very same friction that, you know, is what's going to hold that there. And so in this case, the friction does actually work along the angle of the slope. So in a case where you have gravity wants to go down no matter what, but if you have the slope is less steep, then the amount of gravity that is sort of resolved along the slope. So this is kind of, I don't know if how many of you had vectors in math. This is kind of a vector addition thing where the pull of gravity can kind of be separated into perpendicular to the slope and parallel to the slope. And so if the slope is less steep, more of the thing is there's going to be less down. There's going to be less gravity working directly down the slope, but the amount of friction is always on the slope. And so in that case, the resistance of friction might be enough to keep the gravity from pulling the thing down the slope. But on the other hand, if you have a really, really steep slope, straight down is more aligned with the angle of the slope. So basically, the closer down is aligned with the angle of the slope, the more gravity is going to pull down as opposed to in towards the earth, and the less friction is going to be able to resist that. So the steeper something is, the more gravity is going to act on it. I mean, the more gravity is going to pull down. But also, the steeper it is, the less friction is going to be able to resist. So does that make sense, first of all? Do you understand what I'm saying about how you can split that vector of just down into along the slope and away from the slope? Cool. All right, so if that is confusing later, just feel free to ask later or ask on email or in office hours. But basically, the friction versus gravity is kind of the deal here. But what's controlling the friction is what the different rocks are, like what is in there. You can have rocks that are much more rough or rocks that are much more slippery. You can have an interface of really sticky rock with really slippery sediment. A lot of it depends on what is sliding past what. They'll have different kinds of friction and therefore a different amount of resistance. But in general, so it's that combination of gravity wants to pull down, friction doesn't want to be pulled down. But if the force of gravity becomes stronger than the force of friction, either because this thing gets too heavy, or because the slope is too steep, or because something changes how stuck together the rocks are, then sometimes friction will win, sometimes gravity will win. And so so whenever a slope is not failing, which is most of the time, friction is winning. But again, a number of things can make it, can kind of tip the delicate balance and cause gravity to win instead. So does that concept make sense before I go on? Okay, I see some thumbs up. I don't hear anyone saying no, so I'm going to go on. So this is different for every slope. Every slope is kind of its own thing. So every slope exists at what we call its angle of repose. And so that's the steepest angle, or most slopes do. That's the steepest angle that that slope can exist at without collapsing. So that's a thing where that is the angle where friction just barely wins over gravity. And now there are places where slopes are a lot less than their angle of repose, especially in places like the East Coast, where there aren't any plate tectonics really causing new landforms to grow. And so it's just erosion and things getting smaller. But for the most part, especially in a place like California or in a place on a plate boundary, where in our case, a lot of our mountains are getting bigger all the time, slopes exist at the angle of repose. So that's where is friction resisting gravity, but sometimes just barely. And so mostly that angle depends on what the hill is made of. So for these example, it uses just some piles of sediment rather than rock. So like well-rounded sand, because it's small and it's rounded, so it's super smooth, that's going to slide really easily. It's very easy to make a bunch of little round things roll down a hill, right? And so the angle for sand, and especially dry sand, is going to be pretty low. Whereas if you think about something like irregular gravel, which is larger and chunkier and has a lot more sticky edges, it's a lot easier to pile that up and have the different chunks of gravel kind of grab onto the irregular bits of the other and stay in a steeper pile. So does that idea make sense? Cool. And so sometimes the angle of repose will be, it'll stay the same on a hill for a long time. But sometimes, like let's say you have a really big rainstorm and it introduces a lot of water, that might change the weight and both change how sticky something is, but also how heavy something is. So making it stickier might make it harder for it to slide, but making it heavier might make it easier for it to slide. Or let's say you have something that's just straight up a pile of granite, doesn't have any chunks in it, it's just granite. You can have a near vertical angle of repose in granite. Just think about the cliff sides in Yosemite, for example, just nearly vertical, and those are solid granite. But like, let's say you have an earthquake and it cracks, introducing a new weakness might make something fail. But for the most part, if you see a hill, especially here in California, it's going to be just barely not falling down, which sounds terrifying, but at the same time, it also does take a lot to make it fall down. So it's not like every hill is about to kill us. It's just it's a sort of long-term, a delicate but long-term balance between the force of friction and the force of gravity. So does that make sense? So as I was getting at, there are ways to tip the balance, and you get a mass movement when you tip the balance. And I just realized I lost a slide where I was going to ask you some ways that this might happen, but I think we kind of talked about these already. So there are a lot of ways to throw off the balance. You can make the stuff on top heavier, which means that there's more gravitational force acting on it because it's heavier. And so it's going to be more likely to move down. You can change the angle. So sometimes the angle changes by there being a mass movement, there being a landslide, and then the angle is different. And because of the new balance of the hill, it makes it worse. So sometimes you can have one kind of mass movement followed by another one, depending on what the new angle is. Or like you could also change the angle by, say, being Caltrans and wanting to build a new freeway and cutting a road cut. And suddenly you have this nearly vertical thing that just keeps dumping the hill on the freeway. I don't know how many of you go as far east as like Pomona, but that interchange of the 10 and the 57, it feels like there's a landslide on it like every 5 years. It happens like all the time because they cut into a hill that made it very, very steep. And so just adding enough water, it kind of fails like a lot. You can change the internal cohesion. So you can make it stickier by adding water. You can make it drier by removing water. You can add some cracks in it, which makes it stick together less. There are a lot of things you can do for that, although it's usually in the grand scheme of landslides, water that's involved there. You can create a plane of weakness. You can again, this is another case where it's kind of a subset of the internal cohesion thing. Not just anytime you're breaking something up, not only is there's more chunks that can move around, those interfaces, the breaks themselves are weaker. They're weak zones where things are more likely to slide. So things like, an earthquake can cause a plane of weakness. You could just have a plane of weakness from good old weathering. You could have a plane of weakness just along the boundary of two different kinds of rock. There's a lot of ways you can get that. You could, again, create a plane of weakness by being Caltrans and blowing stuff up, or being a miner and just digging things out. Landslides mass movements are actually, of the things we're going to talk about in this class, definitely something that humans influence a lot. They definitely happen in totally natural settings as well, but people can make these worse, absolutely. Another thing, you can remove external stabilizers. So like, let's say there's a big hill and there's a small hill in front of it, and the small hill is kind of working like a doorstop. It's kind of preventing the big hill from falling down. But let's say the small hill collapses because its angle of repose is different. Or let's say, again, Caltrans removes the small hill to put in a freeway. Sometimes there's a lot of external forces. This is also that example of like plants, the plant roots that you mentioned at the beginning. If you burn the plants and they're not alive and their roots aren't holding the ground down anymore, there's less stability. You can add water, which does a lot of these things. It adds mass and it changes the cohesion. Or you can shake it up, because just if you're shaking something, it's going to become unsteady, especially the looser it is. And actually, my background picture today is from Hokkaido, Japan, in 2018. I think that earthquake was 2018. There was an earthquake that caused a ton of slopes to just come falling down. And so every piece of exposed red you see in that image is a place where there was a landslide. All of those were lushly forested green hills before. But because it was a wet time, there was kind of a storm going on at the same time as this strong earthquake. It made like many, many hills in this part of Hokkaido just completely sliding down. So there's a lot of ways to totally screw with the stability of a slope. Many of them natural, and then many humans have made even worse. Yeah, it's totally crazy. When I first saw that photo, I was like jaw dropped. Like, I was teaching a California specific class, and I was like, I don't care, I'm putting this in to show what earthquakes can do, even though it's in Japan. But yeah, a lot of ways to destabilize a slope. And it turns out that the combination of these factors and the stuff that's in the slope to begin with kind of controls what kind of mass movement you get. Yeah, it is a beautiful photo. Luckily, it is not a densely populated place. Hokkaido in general is very sparse. So there were still definitely deaths and loss of property in that earthquake, but nowhere near as bad as it could have been. But I digress. We'll talk more about earthquakes in December. But does anyone have any questions about these ways to destabilize a slope, ways to throw off the balance between gravity and friction? Cool. So we will be coming back to these as we talk about different kinds of mass movements. But yeah, what we're going to get into now is just the many, many different ways that hills and rocks can fall down. Influenced by sedimentary processes, but also part of sedimentary processes. And there's four major types of these things. And we kind of we classify them based on what is moving, like what's falling or sliding. Is it wet or dry? How broken up is it? Based also on how is it moving? Is it falling? Is it sliding? Is it flowing? And then also on how fast it's going. So normally when I assume that, like, when I say landslide in general, like how fast of a thing do you think that is?
I'd say pretty fast, just personally.
Yeah, so is there anyone in here who, when I say landslide, thinks of something really slow? I don't see any response. Yeah, most people do think of them as fast. Like, that's very much the common way of thinking of a landslide. And certainly if you are in Hollywood making a movie about landslides destroying things, you're going to have them be fast because that's way scarier. But there are some things that are instantaneous. There are some that take years. So it really depends. But those categories of what is moving, how is it moving, and how fast are basically what you need to distinguish from these four categories. So the four major categories, which hopefully sound familiar from your vocab thing, are falls, which are exactly what they sound like. It's a free fall. Stuff falls downhill. And it's pretty much just straight down. And so usually when that happens, just because it's falling straight down, it has to have been pretty consolidated and well stuck together to be at a near vertical angle to begin with. So when it falls, it's falling as separate blocks or chunks. It's just a bunch of rock just exactly what it sounds like. Honestly, most of these are exactly what they sound like. A flow then is rather than just falling, it's something that's tumbling down the side of a hill. And rather than as like a solid chunk, it's stuff that's mixed up together. So it's usually dirt and mud and rocks and water. You can occasionally have a dry flow, but it's pretty much always water. These pretty much always are influenced by water. And so it's just a bunch of mud and gunk and rocks cascading down a slope and flowing across a landscape. And they're usually pretty turbulent. So like if you remember when we talked about volcanoes and we talked about lahars, being a thing of just a bunch of volcanic stuff mixed up with water turbulently rolling down the volcano. A flow is, I mean, a lahar is a flow. It's just most flows don't require volcanoes. And flows are what we usually get like in the winter after a big fire season. This is what happens when, again, the plants are all dead and their roots aren't holding the ground down anymore and then it rains and everything comes down. But we'll talk more about that in a few slides. But for the most part, our day-to-day Southern California existence, flows are kind of the most common. Next, you can get a slide, which is also exactly what it sounds like. It's you have something detaches from its source rock and just moves as a chunk and just slides along a surface, can slide along the surface of the ground, slide down the hill. So it's usually coherent. If it breaks up into a lot of smaller chunks, then it can kind of go from a slide to a flow. But it's usually like, if you look at this example, it's just a bunch of stuff. Here it shows like just a chunk of rock that's broken off and is moving. It's usually pretty solid. It can be rock or dirt. It usually retains its shape until it hits the bottom where it all kind of piles up. Also worth noting, falls are really fast. Flows are generally pretty fast. Slides can be pretty slow. And usually they give you a warning. So actually a true landslide is not nearly as dangerous as a fall or a flow sometimes. And then the last kind is called a subside, where just stuff collapses into a void, which I know we all want to do here in 2020. Basically what happens with a subside is it's another vertical movement of stuff falling in separate blocks. But the difference between a fall and a subside is a fall is coming from a cliff and ending up on the ground surface, whereas a subside is collapsing into a hole that was under the surface of the earth, a hole that's usually formed by water. So it's a case where just rather than it being gravity versus friction, in a subside, it's gravity versus how well stuck together that roof over the hole is. And once that roof over the hole isn't strong enough anymore, everything falls in. And you might notice this has a lot of layers in it. These are especially common in sedimentary environments. But does this general distinction make sense? I spill water all over myself talking about water-based things. Anyone, we're going to go through specific examples of all of these categories, but does anyone have any questions just about this, how we classify and these four general groups before I go on? Cool. Okay, so what we're going to do now is go from slow to fast for stuff that involves rock. And then depending on time, we'll talk about avalanches at the end, about snow avalanches. If we don't have time for that, I'll probably just cut it off and we won't worry about it for avalanches for the test, just in the interest of time. But hopefully we'll have time. So yeah, slow to fast, hopefully, if it lets me advance. Okay. So the slowest kind of mass movement is something you're never even going to notice from day to day. And it's something called creep. And creep is technically a type of slide. It's something where the surface of a hill is just slowly moving down the hill. Like the surface layers of usually dirt and unconsolidated sediment are usually moving along their interface with the solid rock inside the hill. And so this is a picture of UC Berkeley, the Berkeley Hills, the Oakland Hills. Like if you've been to the East Bay, you've been in a place that's creeping. But it's so slow that it's not something you'd notice from year to year. Certainly if it was fast enough to be noticeable, nobody would be able to build anything here. But basically just what's happening is water seasonally gets into the soil. And when you add water, it expands, but then when the water dries out, it contracts. And then it rains again and you add water and it expands. And you remove the water, it evaporates and it contracts. So the whole process of creep, and the reason it's called creep is because it's this very slow, gradual, almost indetectable thing, is that it is a contraction and expansion effect. So basically, it does, because if it were just in place, if it were just on a flat surface, it would just kind of like an accordion in place. But because it's on a hill, like when it expands, part of it goes down. And then when it contracts, it goes back up again, but a little bit further away. Like it doesn't go back to exactly where it was because it expands both ways and then contracts both ways and expands both ways and contracts both ways and just slowly inches its way down the hill. Kind of like if you think about like how an inchworm caterpillar moves, it kind of like it lifts itself up and then stretches itself back out to slowly walk along. And that's basically what's happening along a hill that is creeping. So does that make sense? That idea of expanding and contracting. And it's super slow. In fact, the way that we see it isn't like so much by literally watching it move as, oh, I took out that slide. No, I deleted a slide that was showing how people track these from space. I don't know where that slide went. I will put it back. But basically, there's ways to use satellites to see very, very small movements in the ground surface. And that's actually the way that the creep in the Berkeley Hills was discovered, by this very gradual, like fractions of a centimeter to maybe a centimeter or two per year movement. Yeah, it's super cool. The process of using satellites to study the shape of the Earth is called space geodesy. And people use it for landslides, they use it for earthquakes. There's a lot of really cool stuff for that. But yeah, so you might go, okay, this is really slow. Why do we even care about finding out whether it happens? Well, it's still fast enough that it can mess stuff up. So over time, it can cause a lot of deformation. So here's an example of some sedimentary rocks on a creeping hillside. And so you see how all of these beds of rocks kind of curve over at the top. That's caused basically by the movement of the very surface of the hill just dragging along. This is just the very slow failure that over time causes these things to curve and move downhill. Which is fine if it's just rock. Like if it's just rock, who cares, right? But people live on these hills and they build infrastructure there. Like over time, that could cause your power lines to fall down. Or let's say you have gas lines or water lines that are crossing a creeping hill slope. Over time, that might cause small cracks and then bigger cracks and bigger cracks to form in those lines. Or if you see this example here, these trees are having a weird time. Usually this is going slow enough that you'll just get the tree to grow with kind of a slightly bent trunk. But eventually the weird shape of that tree could cause it to fall on things on that hill. Basically, this is a slow process that can still cause gradual damage to infrastructure. And also it does weaken the hill enough that it could eventually become more susceptible to some other more catastrophic kind of mass movement. But does that all make sense? Does anyone have any questions about creep? which I don't have videos of because it's so slow. Cool. Let's go on to stuff that's fast.
I
Oh,
have
yeah.
a question. Can people, you know how you said people live on these environments?
Yep.
Can they feel it like slowly happening?
No, it's way too slow. Like we're talking, it moves at a speed of like maybe a centimeter per year. It's really, really, really slow. Kind of the only way to see it is honestly through either if you're specifically putting something there to get bent and deformed and show that it's moving, or looking at it from space. Like honestly, the satellite geodesy thing, and I will put that slide back in. I don't know why my slides are sometimes disappearing. Excuse me, but I will put that slide back in before I post this on Canvas. But yeah, honestly, the fact that creep is so widespread wasn't even really discovered until satellite geodesy became a thing. Does that answer your question?
Yeah, thank you.
Definitely, if it were fast enough to feel, people would be like, I'm not building on that. Yeah, cool. Let's move on to some stuff that is fast enough to feel. So the next kind of thing we're going to talk about is called a slump, which is something we all feel by the end of the semester, but also is a kind of mass movement. And so a slump is another kind of slide. It's another thing where you have a solid, pretty well consolidated thing that is moving along an interface and retaining its shape pretty well. But while creep is really just the surface layer and is moving by expansion and contraction, a slump is a much larger scoop out of a hillside. So this is a case, so you can see this is a hillside. I guess it's also a hillslide. This is in the town of La Conchita. So this is right on the 101, kind of if you're driving to Santa Barbara. It's a little bit, it's sort of between Ventura and Santa Barbara on the 101. And you can actually totally still see this thing. Basically what happens is this is a case where there's some sort of internal weakness in the hill. And all of this is sediment. Like I wouldn't even necessarily call this sedimentary rock yet. It's sediment that is maybe in the process of lithifying, but ultimately it's close enough to the surface. It's just kind of densely packed sediment. And what happens is usually, it's pretty much always water in this case, gets in there and makes the hillside heavier and also slicker because you add water, it makes it slippery. And so you have a case where it's heavier and more slippery. And in that case, if there's just a little bit of a plane of weakness in the hill, that's just going to scoop out and move along that plane of weakness until it reaches an angle where it's back at repose. So you notice, even though this scooped out, you can see there's this big gap at the top of the hill. It didn't it did absolutely destroy some houses. Nobody died in this because they're slow. These are very slow. Nobody died in this, but you can see that even though this slid out some, it didn't just like keep going until it was flat. Now it stopped because it turns out that this was the appropriate angle of repose for this chunk of the hillside. So does that make sense? So these, when they happen, well, actually, I'll talk a little bit more about the anatomy of a slump because they have a very specific shape and it kind of controls why we can tell they're about to happen. So a slump always has a very specific anatomy. So the sliding surface is usually shaped like a scoop or a spoon. Like if you were to take an ice cream scoop and gouge out part of this hill, it would make a shape like, if you think of scooping ice cream, a slump is actually going to follow a shape very much like that. And so the sliding surface is what we call the basal surface because it's at the base. And so as things slide, you see what's called the head scarp. So a scarp is basically a cliff, kind of a long linear ridge caused by ground failure. And so you'll have the head scarp, which is at the top. It's where things detached. Then the top of the thing is called the head and the bottom is called the foot. And so what will happen is all of this stuff will flow along the basal surface, along this curved line, and usually overspill it a little. And so the part that overspills, like the part that's still in that scoop, is called the foot. But then the part that spills out onto the ground below is called the toe or the tip. And so that's just going to keep moving kind of as long as momentum carries it. And so basically, you don't need to know all of these little words. I want you to know basal surface, head scarp, foot, toe. But the important thing about this is when one of these starts, it doesn't all happen at once. Usually the head scarp will start to form, and there will be some cracks along the future head scarp before anything else starts to move. It's a slow process of failure. And so usually, and also it usually happens after very wet weather, and you can get some sense that it's about to happen. So people will see a head scarp start to form and be like, GTFO everyone, it's gonna go. And then usually it moves honestly slow enough that it's kind of hard to get a video of a slump. It can take hours or even days. I think the one in La Conchita took a matter of like 5 or 6 hours to go from a consolidated slope into that. And so the people in these houses, yeah, their houses were totally destroyed, but they were, everyone in the town was able to evacuate because people saw this head scarp up here starting to form before everything happened. So does that make sense? The movement of a slump is actually, rather than just sliding, it's kind of rotation. Because the basal surface or failure surface is curved usually. It's again, think of like taking an ice cream scoop and just scooping out some ice cream. And now I really want ice cream and might have some after class. But it's that idea of you don't just like pull the ice cream off. You have to scoop it out with something rounded. And in order to pull it out, you actually kind of have to rotate the scoop. And that's exactly what happens with a slump. There's the center of gravity of the slump is based on just kind of how much stuff there is. And as soon as it gets thrown off, it just kind of slides out and pours over. So I would like you to sort of remember that a slump it's a slide, but it's a rotational slide rather than just slipping. Does that make sense? And if you have ice cream, feel free to go get some. I don't mind if you eat during my class. But yeah, any other questions about slumps? So before we go on looking at this slump though, so this is a slope and this is a less slope. But now look at the head scarp and look at the toe. What is the angle of the toe and of the head scarp like compared to the angle of the rest of the stuff that moved?
Can you repeat the question, please?
So look at the angle of the head scarp and the angle of the toe and compare them both to the angle of the rest of the stuff and the angle of the pre-slide surface. Like, how does it compare? Is it a bigger or smaller slope?
It's a smaller slope, right?
Or let me phrase that better. It's a smaller height, but is it a steeper or shallower angle?
Oh, I'm gonna say shallower.
So are these closer or further from vertical than this?
You're saying the original one?
Either the original or the, I guess compare it to the post-slide surface, just to this.
That is not closer to vertical. Oh, actually, wait. No, it's not.
The head, so so you're saying that the head and the toe are less vertical than the post-slide surface? Whoops.
Oh, this is hard. I'm sorry. I'm not.
So so when I think about, so actually, no, it's good that we're stuck here because I want to make sure I explain it well. So if you have let's see if I can draw a vertical line. So there's a mostly vertical line, mostly vertical line, mostly vertical line. So say A, B, and C. Of those three lines, of these three slopes, let me switch colors if it'll let me. So of slope A, okay, pretend that's following this line, A, B, and C. Which is closer to vertical, A and C or B?
B.
So is B, yeah, A and C. So it's vertical is up and down. Which is closer to up and down?
A and C.
Yeah, A and C. I'm sorry if I phrased this badly. So basically the closer to up or down, the closer to up and down it is, the more likely it is to fall, right? Because if you remember from way back, the more vertical, the more up and down something is, the more gravity is directly acting along the slope. Does that make sense?
Yes.
And also, reminder is that like if I'm asking, does that make sense? That is absolutely 100% time, your time to say no. Like I'm asking because I want to make sure you have it, not because I expect that you have it, if that makes sense. Like, but yeah. So if this has happened and now these parts are closer to up and down, don't you think that could be a problem? It's definitely a possible problem. Because even though this part of the slope is now further from failure, even though this part is now at its angle of repose, it's created two new slopes that are very, very steep and could therefore also fail. And as it turns out, they often do. But does anyone have any questions about that before I go on to the next kind of slope, failure that often happens in situations like this? All right, so this is also La Conchita, and this is at the toe of the slump from the other slide. So very often where you get a new steep slope, you get other kinds of flows. And so what we're going to talk about now is, and this is a couple years later. And so a mud flow or a debris flow is very common in Southern California. It's also a flow, or in this case, it's a flow rather than a slide. And so in this case, it's mud and debris and water and rocks and stuff mixing up with water and just pouring and flowing along the surface. And these absolutely require water to flow. But in this case, they can be pretty fast. The speed depends on how much water and how steep the slope is. And yeah, this one absolutely did bury those houses. And these are very fast, and people did die in this one. These give very little warning. It's, even though this kind of looks like a headscarp, all of this happened so quickly that they didn't have time. And by the way, this down here, this is the 101. So this was very close to the freeway. But yeah, these are scary because they can happen with very little warning and can happen very, very quickly. These are very dangerous, just precisely because of the not giving much warning. And so a mudslide is honestly better than a debris flow in that it's literally just mud, but a debris flow can have boulders in it. It can have, this happened in like minutes. Yeah, these can be minutes. And sometimes they can last for a long time, kind of depending on how much material there is. But yeah, these are scary. These are bad news. They give very little warning. Certainly you can get a sense of where they're more likely to happen. Like if, let's say you just had a slump and you have a much steeper slope and then it rains, you can kind of have a guess that that might be a place where it would happen. Or very often, if you look at like the next time we get a big rainstorm in an area that's just had a fire, look at those weather alerts and stuff, because they will say there's an elevated chance of debris flows in the places that just burned, both because there's a bunch of burned up stuff, but also because the ground is less stable there and it can flow much more easily with the rain. So this is a particularly large one. These can be small, but these can be very bad. So it's just a bunch of rubble and dirt and mud flowing sometimes as fast as a river down a hill. But just how fast depends on the slope of the hill and the amount of water. So does that make sense? It's pretty straightforward, I think. Stuff flows downhill. Wait, it won't let me play it because I'm on pen. Okay, so here's an example of a debris flow up in the San Bernardino Mountains. Yeah. So that is a boulder the size of a boulder. So this is, in this case, like this is just, you can see why this is a problem, right? Like, I feel like I don't need to describe why this is a problem. So this one is definitely a debris flow because there's lots of large rocks, whereas the La Conchita example is much more of a mud flow. Yeah, a large boulder the size of any kind of boulder. But this is a mud flow because it's really just mud. But that's kind of the only distinction. But yeah, this thing was going really fast. And so, yeah, you have quickly flowing water with large rocks in it. They happen often. On the scale of the examples I just showed, not super often, but generally there are some small ones kind of every year in Southern California. They're very common, usually on a smaller scale, and especially up in the mountains where there's a lot more of a slope and also where it rains a lot more. This is very much a significant hazard around this part of the state. And it's going to probably be a really bad year for them this winter because of all the fires, although probably more in Northern California. But yeah, you've got flowing water, you've got tumbling boulders. And these can not just, they can really cause a lot of problems. Like this is Forest Falls up in the San Bernardino Mountains. This was a particularly devastating one in the late 90s, if I remember correctly. In this case, this debris flow just blasted out the size of this house. Like a house is not, especially a wood frame house, is not going to win against flowing mud full of boulders. And in this case, this is a big old pine tree, and this bark got scoured off by the debris flow scraping past the tree. These things are really scary. They're really bad news. But for the most part, if you're not living in or up against the mountains, you have less to worry about. But yeah, these are scary and they're fast. So does that make sense? And any questions about, the way to stop them, there's no way to literally stop them. I mean, if you see what this did to this house, but very often people will try to channelize them. They'll try to dig ditches where they think one is going to come from and hope that it stays in the ditch rather than going into a town like this. But again, if there's just too much stuff, there's very little you can do. Any other questions about these? Right. Let's keep going. So another thing that's pretty fast is a rock slide or a debris slide. And so in this case, rather than flowing, it's sliding. So in this case, like you can see here, see these sedimentary beds, see how these rocks are in layers but at an angle? And then see how there's this big old scoop out right here? And then see how there's chunks of rock in the water? I think this is actually also along the 101, if I remember correctly. But basically what happened is just along these boundaries between the layers of rock, just this got weak enough that over time, just other layers slid off into the ocean, just sliding right along the surface of the other rock as a discrete block. Like, I mean, this has probably been weathered by the ocean a lot now, but you could probably, if you were the Hulk, I guess, pick that up and fit it back into the chunk that it fell out of. And so this is a pretty small one. Like, I mean, you still wouldn't want to be standing next to this. You would not when it was happening. But this is a pretty small one. And so, but basically, yeah, this is, solid or shattered rock moving along a plane of weakness. In this case, the ocean is here, but water isn't actually necessary. This is really just over time boundaries between layers of rock, or boundaries with cracks in the rock, just weakening over time until gravity wins. And these usually give some warning. They usually, again, you'll see cracking and you might hear things. So usually, like, it wouldn't go from solid to that in a fraction of a second, but once it starts sliding, like once the warning signs have started, you GTFO, because once it starts going, it is going. Yeah, so generally, pre-existing planes of weakness are the best thing for this. So this is the thing where it tends to most often happen in sedimentary rocks where you have those layers. And once you get a crack, things are just going to slide along the layers that already exist. Does that make sense? Cool. So the general term landslide, this is where the general idea, a landslide is this, like the general term landslide applies to this specific case where it's a mass of soil sliding along an interface with a rock. So an example where, like, if you remember how creep was the soil layer creeping along the bedrock, in a landslide, it's the soil and unconsolidated sediment layer just sliding as a unit along the bedrock. And so here's an example from Japan. They knew it was coming. They blocked off the road. Yeah, right. Yeah, so this is a completely bonkers video. Yeah, so that is a true landslide. Yeah. So these give warning signs. They usually also had a headscarp. You can see they were on top of it about blocking off the road and made sure nobody going there. But yeah, they're fast. Once they go, they're fast. This is going to be much faster than a slump or than creep. But yeah, it's literally, it's landsliding. The name, it's exactly what it says on the box. Does anyone have any questions about that?
Yeah.
Could I replay it? At the end of class, because there's still a few more things I need to get through, but yeah, I will totally replay that at the end of class. The land you're standing on should not be able to move. I have bad news about California. But anyway, I will totally play that at the end. But there's a couple of more things that I want to talk about first. Cool. Any other questions about that, though, before we go on?
Yeah. Can, like, an earthquake, if an earthquake happens, can it, like, promote this to happen?
Absolutely. There were thousands of landslides, not necessarily this large. Like, this is an exceptionally big one, but like my background picture from the earthquake in Hokkaido was this kind of thing happening because of an earthquake. Or actually, the 1994 Northridge earthquake caused thousands of landslides in the Santa Susana Mountains and the Santa Monica Mountains. So earthquakes are a very common cause of this. But usually not. This video is an exceptionally big one. Yeah. We might talk about earthquake caused landslides in the earthquakes lectures, but I want to get through just a couple more kinds of other landslides. We good? All right. So the next one, This one is very straightforward. It's a fall. Rock falls off cliff. Rock falls at speed of gravity. Like sucks to be this guy. But basically, it's just something breaks off and falls. Usually it's related to weathering, just causes, especially if you remember all of our physical weathering of things wedging rocks apart. Usually something like that just causes something to detach and it falls. Doesn't need water, and it's gravity. It's just fast. Yeah, I don't. Some insurance has something called an act of God clause that covers things like this. It depends on how good your insurance is. Anyway, there's kind of not a lot to say about this. They do happen. Actually, they're a very common occurrence in places like Yosemite. So this is, they caught one in action in Yosemite in, I think this was 2018 or 2017. And so you can see, yeah, sorry. This will be on Canvas later as well. But did you have a question about this slide, or are you just writing something down? Notes, okay. I mean, so I guess I can keep talking about Yosemite. This is very common at Yosemite just because it's completely vertical granite cliffs, but there's a lot of fires in that area, which cause a lot of cracks in the rock and cause a lot of things to fall. So in this case, they caught this one in action, and it left this big bright scar on the hillside where this piece of rock detached. And you can see like it smashed here and it smashed here and then kind of exploded over the side. And you can see a big pile of debris. And mind you, this is like a 3,000-foot cliff to give you some sense of the scale of this. But physics-wise, it's literally just falling. It's just kind of spectacular. And so the pile of stuff that ends up at the bottom, so this is an example from, I think this is in Washington State. The pile of stuff that ends up at the bottom is called scree or talus. So here's a fall. You can see that this freshly broke and turned into pulverized chunks. And this has probably happened more than once here, looking at the shape of this pile. But the pile of rock at the bottom of a fall is called either a scree pile or a talus pile. But that's kind of it for falls. Any questions about falls? It's very straightforward, this one. Cool. Then I'm going to go on to, we're not going to have time for avalanches today. Don't worry about avalanches for the test, even though it says that on your notes taking guide. But the last one I do want to talk about is sinkholes. So this is an example from, I think it was Guatemala is where this one was. But it's also gravity moving things down. The difference is just that it's moving it into a hole. And usually that hole is caused by groundwater flowing through and removing material. And sometimes it'll even fall into a cavern like the ones we talked about at the beginning of class, where limestone caves fall, like where you get those precipitation from solution kind of rocks. But in this case, this might have been full of water at some point, and then something happened such that the water left and there's a hole. And so anytime you have a hole, the thing that prevents things from falling into it is just the strength of the material on top. And so if over time that material over top weakens just from weathering, just from things going over it, like this one was in a road, so probably the percussiveness of people and bikes and cars going over this didn't help. Just eventually, if there's enough weakening, it's just going to fall into the hole. And this can be gradual. It can actually be a very gradual thing that gives warning, but it can also kind of be all at once. And this one, if I remember correctly, was kind of all at once, but happened at night, and so nobody was in it. But these can be pretty dangerous. But it's very much just water removes material, and then the ground above, just as soon as it fails in strength, it's going to go down. So does that make sense? So this is a very large one. They can also be on a smaller scale, and they can also be kind of man-made. I just said all this, but like this is an example from the street I used to live on when I lived in Riverside. And so at first there was just this little thing, and they were like, oh, that's kind of bad. because they paved a drainage out of a mountain. And so there was water flowing under the street and removing all this material. And so at first they were like, okay, I guess we should fix that. But then it turned out that actually literally the entire street had nothing holding it up. And this was just the first place to fail. And so they took like over a year to fix this, and it was kind of hard to drive on my street. But this is something that happens in nature, but can also be enhanced by people. So with that, I'm done with this. If you have any questions, you can hang out and ask them. I can totally play that other video again. Also, if anyone wants to hang out, I have cool Avalanche videos that I can totally play. But if not, I will see you all on, today is Wednesday, right? I will see you on Monday, and we're going to talk about rivers and floods.
Bye, Professor. Thank you.
Talk to you later.
Thank you, Professor. Have a good day.
Let's go back to that crazy video. And the video will be on Canvas too, in the PowerPoint.
Actually, I have a question about the avalanche.
Yeah.
So an avalanche, what makes that different from like what you're showing right now, a landslide? Is it more
an avalanche is snow.
Oh, that's it?
Yeah.
Okay.
So there's actually two different kinds of avalanche. One of them behaves like a slide and one of them behaves like a flow. It's just the difference is that it's snow rather than rock. So like the term rock avalanche is not really a thing. Like it's a rock fall or a rock slide. Yeah, this video, every time I watch this video, I'm like, holy crap. You want to see the avalanche videos?
Sure. Yes, please.
Yeah, so avalanches, as I was going to end with, they're very popular for killing off characters in fiction. It can be a flow or a slide. So like a slab avalanche is when it's kind of a slide. And so this guy's deliberately trying to cause one. You're going to see the headscarp form as he, sometimes you want to cause them to make the slopes safer. So you're going to start to see a headscarp. There we go. There we go. Yeah. So like a rock slide is going to behave in very much the same way, just with rocks instead of snow. So yeah, did you see the scarp form and then everything start to move?
Yeah.
Probably 6.
Yeah, so, and now you can see the remnants of the headscarp up here. So that same idea is like with that absolutely bonkers landslide in Japan. They probably saw like cracks like that start to form before the hill gave way and they knew to block it off. Usually avalanches are faster than slides or like landslides, but yeah, you can see even though he was trying to cause it, he's having a little bit of a hard time there. Yeah, so that is a slab avalanche where, I mean, by the bottom it's broken up because it's hitting the ground, but for the most part it's still moving as a solid sheet. So it's a slide. But a loose snow avalanche is where the snow flows like a debris flow. And so in this case, this is from Switzerland, and they're also trying to make this slopes less dangerous. And so in order to cause some avalanches, they're gonna blow some stuff up. I forget exactly when it starts though. Forget exactly when it starts, otherwise I would fast forward it. There we go, explosions. And watch what happens next. So do you see this kind of pouring down the hill over there? So in this, like this, you see how this looks super different from the other one, right? See how it's going back up because it's propelled by the power of the flow within it. And so like debris flows can do this. Pyroclastic flows can do this. It's just, this is all snow. So this is,
Det är snö som kommer ner.
yeah,
Det är inte bara snö ser det ut.
it's going across the water because it has so much internal propulsion.
Is all of that snow?
Yep, all snow.
Oh my
I mean,
god.
probably some of it. Why are they so close? Because they're crazy. I guess they're living on the edge. I don't know. I mean, definitely like by the time it reaches something flat, it's nowhere near as dangerous as a mud flow or a pyroclastic. I mean, the pyroclastic flow would have killed you if you were that close. Like you can see by this point, it's not moving very fast. I don't know if it could knock them over. Certainly if you're closer to it, like if you were up near the top when that started, absolutely. It's kind of why it's a popular way to wipe out people in fiction. But at the same time, people do survive these. Like this is, if you're gonna be hit by a flow, probably better a snow flow than a mud flow or a debris flow. But yeah, this is just, some of this might be vapor by this point. I think of the flow in Mulan, yeah. Yeah, so, yeah. That was, I mean, so the avalanche stuff not going to be on the test since we didn't talk about it in lecture. But if you do want to watch these videos again, it will be on Canvas. There's a lot of videos of ski resorts trying to do absolutely crazy shit to make avalanches happen so it doesn't hit skiers. But yeah, that's what I got. Do any of you have any questions about that or about anything else we talked about today? Yeah, have a good one.
I have a question.
Yeah.
Is our test next Monday?
No, it's the Monday after. It's the 9th.
Got it. Okay.
Yeah, and when in doubt, it's on Canvas.
Okay. Thank you so much.
Have a good one.
You have a good one too. Thank you
Yes.
for terrifying me about the moving soil underneath my feet.
So it's so California has many ways the Earth can move around. Earthquakes we'll talk about later.
Well, when I say that, I just mean like, I don't know why, but like in my brain, rock should not move. It should stay still forever, but
I
it
mean-
does, and that freaks me out.
I mean, rocks are actually moving literally all the time because of plate tectonics.
And that is messing with me.
But it's slow enough that like 99.99999% of the time, you're never going to feel it. It's just those moments when it goes way faster. No, I mean, these are scary. They're scary. There's a reason that like these are a natural disaster. These are damaging things. They cause problems. There's a reason that places get closed for years due to landslide damage. Like they're dangerous. But
Yeah. Well, anyway.
it's one of those things that like, if you're ever in a situation where you're like buying a house or even just choosing a place to rent, don't be at the very top or the very bottom of the hill.
Good advice.
Yeah, especially not in Southern California. Like a place like San Francisco is not going to be so much of an issue. But a place like, the foothills, like around Pasadena, Altadena, the further up in the mountains you go, the worse it is. Like,
Got it.
but the state actually has a hazard zoning. There's a thing called, it's the Seismic Hazard Zoning Act because it started due to earthquake related landslides. But there isn't a thing where if you're looking for a place to live, there are maps of the entire state that basically say this is a place that's more likely to have landslides. So those are maps that anyone can access. So
That is really helpful.
yeah, so it's partly it mostly exists for how people are going to build stuff or not, like for developers to go, maybe don't build something there, or if you are going to build something there, you have to take these extra precautions. But certainly, like if you're looking for a place to move, because California has so many ways where the earth can kill you, there are a lot of, there are zoning maps for most hazards at this point. There are earthquake zoning maps, flood zoning maps, fire zoning. No, there are not fire zoning maps. But there's earthquake map, landslide maps, tsunami maps, flood maps. There's a lot of things. There are volcano maps for the places that have volcanoes in Northern California. But the fires thing is just, it's kind of impossible.
Yeah, it's realistically speaking, we should be able to list some places of how as fire zones, but there
I mean, there are places like the further into the forest you get, the more likely the fire is.
most definitely, yeah.
But and also when you live in a place where people are like, wow, the wind is blowing really, really hard, but the Dodgers won the World Series, so I'm going to blow stuff up. When you end up in a situation like that, you're kind of like, there could be a fire anywhere.
Yeah, should I classify this whole area as a fire zone? Just when
Honestly,
the Dodgers
Southern
win?
California, yes.
Oh,
Honestly,
okay.
California in general, yes. I wish that we had time to talk about fires in this class, because they are very much a process that happens in California. But because this is geology and rocks focused and not technically a California specific class, it was one of those just like not time for that in this class. But if you do need other gen eds, like if you need an upper division natural science gen ed and want to be more informed about California in particular, Geology 344 is specifically about California geology, and we do talk about fires. And if you need another lower division one, which I think you probably don't, but if you need another lower division physical science class, Geology 117 is specifically about natural hazards and disasters. I think that's the name of the class, is natural hazards. Yeah. If you need an upper division natural science gen ed and like this stuff and want to know about California, 344 is totally the way to go.
Okay. Thank you, Professor. Have a good one.
Thank you. Yeah, have a good one. For the rest of you, for Matt, Eli, and Mario, are you just hanging out? I'm going to take it as just hanging out. If you do have questions, just let me know on email, and I'll see you Monday.